30-second adventures in thought. Number 6. Schrödinger's cat. Erwin Schrödinger was a physicist, a theoretical biologist, and probably more of a dog person. In the 1920s, scientists discovered quantum mechanics, which said that some particles are so tiny you can't even measure them without changing them. But the theory only worked if, before you measure them, the particle is in a superposition of every possible state all at the same time. To tackle that, Schrödinger imagined a cat in a box, with a radioactive particle and a Geiger counter attached to a vial of poison. If the particle decays, it triggers the Geiger counter, releases the poison, and bye-bye tiddles. But if the particle is in two states, both decayed and not decayed, the cat is also in two states, both dead and not dead, until someone looks in the box. In practice, it's impossible to put a cat into a superposition. You'd have the animal rights lobby up in arms. But you can isolate atoms, and they do seem to be in two states at once. Quantum mechanics challenges our whole perception of reality, so maybe it's understandable that Schrödinger himself decided he didn't like it, and was sorry he ever started on about cats.
Let me briefly describe the difference between a quantum computer and a regular computer at some level. In a regular computer, you've got ones and zeros, which you store in binary form and you manipulate them, and they do calculations. You can store them, for example, in a way that at least I can argue simply. Let's say you have an elementary particle that's spinning. If it's spinning and that we say it's spinning is pointing up or down, depending upon whether it's spinning this way or this way. Pointing up or down. And so I could store the information by having lots of particles and some of them spinning up and some of them spinning down, right? Ones and zeros. But in the quantum world, it turns out that particles like electrons are actually spinning in all directions at the same time. One of the weird aspects of quantum mechanics. We may measure, by doing a measurement of an electron, find it's spinning this way. But before we did the measurement, it was spinning this way and that way, all at the same time. Sounds crazy, but true. Now, that means if the electron's spinning in many different directions at the same time, if we don't actually measure it, it can be doing many computations at the same time. And so a quantum computer is based on manipulating the state of particles like electrons so that during the calculation, many different calculations are being performed at the same time and only making a measurement at the end of the computation. So we exploit that fact of quantum mechanics that particles can do many things at the same time to do many computations at the same time. And that's what would make a quantum computer so powerful. One of the reasons it's so difficult to make a quantum computer, and one of the reasons I'm a little skeptical at the moment, is that the reason the quantum world seems so strange to us is that we don't behave quantum mechanically. I don't, you can, not me, but you could run towards the wall behind us from now to the end of the universe and bang your head into it and you just get a tremendous headache. But if you're an electron, there's a probability if I throw it towards the wall that it will disappear and appear on the other side. Do something called quantum tunneling. Okay? Those weird quantum behaviors are manifest on small scales. We don't obey them, have those behaviors, because we're large classical objects. And the laws of quantum mechanics tell us in some sense that when you have many particles interacting, at some level, those weird quantum mechanical correlations that produce all the strange phenomena wash away. And so in order to have a quantum mechanical state where you can distinctly utilize and exploit those weird quantum properties, in some sense you have to isolate that system from all of its environment, because if it interacts with the environment, the quantum mechanical weirdness sort of washes away. And that's the problem with a quantum computer. You want to make this macroscopic object, you want to keep it behaving quantum mechanically, which means isolating it very carefully from within itself, all the interactions, and the outside world. And that's the hard part, is isolating things enough to maintain this, what's called quantum coherence. And that's the challenge, and it's a huge challenge. But the potential is unbelievably great. Once you can engineer materials on a scale where quantum mechanical properties are important, a whole new world of phenomena open up to you. And you might be able to, as we say, if we created a quantum computer, and I must admit, I'm skeptical that we'll be able to do that in the near term, but if we could, we'd be able to do computations in a finite time that would take longer than the age of the universe right now. We'd be able to do strange and wonderful things. And of course, if you ask me, what's the next big breakthrough? I'll tell you what I always tell people, which is if I knew, I'd be doing it right now. This way, you've got a box and you can put an object in the box. In the quantum case, there's more than one way to open the box. And you've got to make a choice. If you open door number 1, you'll never know what would have happened. It cannot be known what would have happened if you had opened door number 2 instead. Those are incompatible things. That's something really new compared to classical physics. That's what I mean when I say it's really intrinsic randomness. It's not that there's some record somewhere, but you haven't looked at it yet. There's no record. It hasn't been decided yet whether it's going to be 0 or 1. It's not until you make the observation and open the door that it becomes the value of this bit. Maybe it's a 0, maybe it's a 1.
The randomness comes from the ability of quantum states to be in a superposition, to be both in the state of 0, of definite, like say spin up or some like particle, and also a spin down state. What if they were not just numbers, they were waves, right? And you can like put together 2 of these waves, and you can think of having half of a 0 and half of a 1. So whenever you measure it, you will end up getting half of the time the 0 and half of the time the 1. So superposition is fundamental for that randomness.
Complete description of the system that is possible, compatible with quantum physics, like when I prepared the state and when we open door number 2, we don't know whether it was a 0 or 1. That's superposition, because that's really intrinsic randomness instead of probability associated with ignorance.
So it takes 2 to tango in quantum entanglement, right? You cannot just have a single qubit and say, oh, it's entangled with what? So you need 2 qubits, at least.
The reason these quantum correlations are different than classical correlations is because we have these distinct, incompatible ways of observing the system. Classical systems can be correlated. We can flip 2 coins and they're either both heads or they're both tails. No big deal. But there's just one way to look at that coin. The qubits are different. We have these 2 incompatible ways of looking at them. They have 2 ways to be correlated, either the same or different for 2 different sets of doors. Those are altogether 4 possibilities, and that means the correlations are richer. They're more interesting. And the richness of the correlation increases very markedly as you increase the number of parts or add additional qubits. You know, if you have just a few hundred qubits and you want to write down a complete description of all those correlations among those qubits in terms of classical bits, you'd have to write down more numbers than the number of atoms in the visible universe.
It's one of these things like, I don't know if it was Faust that said it, that achieving perfection is hard, but remaining perfect, that's impossible. A lot of what we're trying to do also create things that are stable, right? Because you can have the most exotic quantum state, but unless you can probe it, measure it, evolve it in some way that you want, steer it, it's going to be useless.
There's a central problem, and that is if you're running a quantum computation, if you're performing a sequence of operations, processing quantum states, that has to be very well concealed, not just from you and from Spiros and from me, but from the whole outside world. Classically, there'd be nothing wrong with looking in every time step what the state of the computer is. That wouldn't prevent the computer from getting the right answer. But quantumly, if we keep looking at the computer, that will destroy these delicate superpositions. It's a secret computation. Until the end, when we're finally ready to get the result out, we make a measurement. And then it's okay to tell everybody what the outcome is, to broadcast it to your friends. So we can't be looking at the computer while it's performing the computation. If we ask it afterward, what did you just do when you factored that huge number? It should say, I don't remember, because there was no record left behind of what it was doing at intermediate stages of the computation. And this is what makes it so challenging, because we can't allow any leakage of information from the computer to the surroundings. That would destroy the quantum computer. That's what we call decoherence. It's the big enemy. There's a whole quantum world out there which is largely unexplored, because it's only now, within the last decade or so, that we are developing the technological capability to scale up quantum systems, to manipulate them, and we're not exactly sure what that's going to lead to, but we think it's exciting. And I do get excited.
Google and NASA have teamed up to share one of the world's first commercial quantum computers. This machine, made by Canada's D-Wave, will be installed in a NASA research center in California.
This is the inside of one of our dilution refrigerators. All of this infrastructure is to basically operate the chip at a temperature that's 2 orders of magnitude colder than interstellar space. The processor is a quantum computer.
It uses things called qubits, as well as being either 1 or a 0. A qubit can also be both at the same time, therefore bringing about a quantum leap in terms of power.
Harnessing principles of reality that are, up until very recently, completely not observable by us is just fascinating in ways that I can't completely articulate.
The overwhelmingly obvious killer app for quantum computation is optimization.
Optimization problems are extremely difficult problems.
Actually, all Google server centers together will not be capable of coming up with the best solution to these optimization problems as they get larger. So now, what is an optimization problem? Here, I'll give you an example. You want to do a trip through South America and you want to visit a number of cities. And then you ask, what is the cheapest ticket I can get to visit, let's say, 20 cities? And you can, of course, different routes and different airlines. And sort of imagine I list all the different options I have for my different routes to travel to these cities.
We currently, as a civilization, we generate vast amounts of data. It could be climate data, genomic data, but it's very difficult to generate useful insights oftentimes from that data.
If you can solve optimization problems better, you have an important resource at your hand.
I think at least it teaches us that we shouldn't be naive about our world, that we shouldn't think about the world as a simple machine. It forces us to consider, more sophisticated notions of how the reality around us is actually shaped.
I can't ask it how long I'll live or the meaning of life. Really, we don't know what the best questions are to ask that computer. That's exactly what we're trying to understand now.
To me, the most important question is, are we alone? And I have a feeling that quantum computers, as they mature, are going to help us answer that question.
This is, of course, a more long-term research endeavor, and there are still tremendous obstacles and big questions. Some of those will be addressed in D-Wave, some will be addressed at NASA, and some at Google.